on this computer. Okay, now I'm recording. And so I'm going to post this somewhere later. I haven't figured out where yet. But now let me start sharing my screen again. Sorry. Guess I'm a little rusty at this. Okay, now we're recording and I'm sharing. All right, folks, so thanks for being here. So I promised that I would tell everybody about this brand new study that I have coming out. And I'm quite excited about this. And I'm excited to tell you about it too. Just to blow some smoke up my own butt, I've been talking about this study to reporters for the last week. And so next week, when this officially comes out, you're definitely going to hear about it. It's going to make the rounds. It's going to be on everybody's Facebook groups. All your friends are going to send it to you. So this is sort of a good chance for you to sort of hear the goods before it all comes out. It is going to be everywhere. As you can tell from the title, I mean, it's a really, we actually found what the title shows. And so it's one of those, this is going to be like probably my biggest study in my entire career, because it's such a cool finding. And I'm probably the most excited about this one than I have for any other project that I've ever done, because this finding, what we found here, not only provides like a I'm getting ahead of myself, but I'm really excited about this, as you can tell. So let me so what I've done here is I've put together a very small presentation, which is basically like snippets of the paper and some graphs and some pictures. And I'm going to try to sort of walk you guys through what we did with this project, what and why, and what we found. So if anybody has any questions, feel free to ask. I can't see the comments from here, so I have to just sort of speak up. Maybe, yeah, make sure you guys are on mute so there's no distractions. And I just put these slides together this morning. So here's where the paper is going to be next week. It's going to be in the journal called PLOS One, the Public Library of Science. And that is a fully online, freely downloadable journal where you can look and you can see the entire thing you can read the entire thing from start to finish. I'm the first author of this paper. But really I was one of a team of people, as you can see from the authors, that put this whole thing together. This team, we've been working on this paper, this project, for about 2 years now. And so it's been quite a journey, to say the least. What we've published here with this first part is really just one of many of our different experiments that we've done. And so I see this collaboration that we have here as going forward for many years, because it's been really fun. June 21st is the day, that's next Wednesday. And as you can see, I've been talking to everybody already. These are just the outlets I've talked to just now, like in the last couple of days. So it's probably going to be everywhere. So let me get into the background a bit more. I mean, as you well know, I study monarchs, and I've been studying monarchs for many years now. But this paper here is a collaboration between myself, plus these folks here two of them are actually aerospace engineers, of all things. And it's been really fun to work with them. This is one of them. He's my partner in crime with this project, Mustafa. He is a professor at this school, New Mexico Tech, in New Mexico, obviously. And it's a mechanical engineering school. And he is a researcher who works within the field of bioinspiration, which is like a cool word that describes what he does. His work, he's interested in how to build better flying machines, of all things. And what he does is he looks to nature to get the bio-inspiration, quote unquote, to learn how nature and animals have solved various sort of aerodynamic problems. And then he uses that information to apply it to like drone technology and even, outer space drones and really cool stuff. And so he's an engineer by training, but he's, definitely has dabbled in a lot of other fields as well. You may or may not have seen this guy already because like everything this guy does is just fantastic. And one of his latest projects, you may have heard of this one, was where he built a drone out of bird feathers and like a bird, a taxidermy bird, basically. And it was a mechanical drone that flapped its wings, and this is it. And this was like 2 or 3 months ago where he wrote a paper on this, and he described how it works, and he has videos, and this thing kind of blew up, and he went viral for this project. And you probably saw the news. If you just Google like bird drone, you'll find this news articles about this project everywhere. I mean, it went around the world. He said he talked to like hundreds of different journalists from around the world, and everybody was just freaking out about this project because maybe it was because people thought these were bird drones being used to spy on people or what have you. But really, his interest in this was to sort of learn from the birds themselves and how they have solved the world of aerodynamics. This is just some background on my collaborator here, because as you can tell, this research on their side, it's all about how things fly, right? These are just some random pictures I pulled from his own lab website to sort of show you what kinds of things that they work on. And it's all over the place, right? But it's all flying machines. And as you can tell, they capitalize on sort of learning from animals. And they not only study the animals, but then they also like build them. Like this is like literally a robotic fly. And they also study planetary exploration by drones, right? They build drones that could be used on Mars. And so really fantastic, out of this world stuff. And it's been really fun to collaborate with them because they are sort of teaching me all the ins and outs about aerodynamics and physics and airflow and stuff like that. And meanwhile, I'm sort of trying to keep up and then trying to also tell them about how butterflies fly. So that's sort of the background of my colleagues here on this project. This was a collaboration between myself, the butterfly people, plus the aerospace engineer people to come up with this one paper here. So let me tell you a little bit about what Mostafa and his team have found so far with some of this work on birds. So their team in the last 5 years, they've done some really cool work experimentally showing how birds can actually improve their aerodynamic performance simply because of the colors of their wings. And this is sort of the inspiration behind this whole project here. So Mostafa and his team have published a couple of papers already that sort of show either using actual measurements of birds or like bird skins or computational mathematics. They've basically shown that when an animal with a wing that is black, with a black-winged animal like this albatross, they actually get an aerodynamic benefit because the black heats up in the sunlight. And simply because of physics, right? Like if you sit in a car on a car seat that's been in the sun for a while, if it's a black car seat, you're going to scorch your butt, right? Simply because of physics, black surfaces tend to heat up faster. And that heating of the black surface actually creates a micro zone above the wing of heated air. And that heated air is actually less dense and it allows the wing to pass underneath it easier and so that there's basically less drag, less air resistance in the heated surface. So the long story short here is that a black wing has an aerodynamic benefit. And so Mustafa and his team have sort of gone around and looked at all the different bird species there are out there. And they've realized and concluded that a lot of bird species are already capitalizing on this color effect, like albatrosses, but there's other seabirds out there that have long distance flights. And it's especially pronounced in the animals that do a lot of soaring, like albatrosses. And so it's the soaring flight that seems to be where you get the best benefit, obviously because the wings are absorbing the sunlight. And so that's where we came in. So early on, a few years ago, Mustafa and I sort of crossed paths a bit. He had read some of my earlier work on monarch migrations, and especially some of my work that sort of showed how wing color of monarchs is important for their migration. I had shown in a few earlier projects that the color of the orange, the actual shade of the orange of the wings, seems to be important for monarch migration. And at the time, I kind of thought that it was more of like a correlate of flight ability, like those monarchs that are simply good at producing pigment are better at simply flying. And so I thought it was more of a correlational thing. But anyway, he cued in on some of my earlier work. I saw some of their work, and then we got together, and it was, we realized we were working on similar topics. And so then we began this collaboration looking into monarch butterfly migrations. And really, if you think about it, the monarch is like the perfect flying machine because they make this tremendous migration from as far north as Canada all the way down to these sites here. In one, like I'm talking about the fall migration going south, in one fell swoop for 2 months, these butterflies are doing nothing but flying every day, or every day that is it's worth flying. And they're the size of they weigh as much as a paperclip. So really, it's the perfect flying machine. And so monarchs, through their evolution over eons, have basically solved a lot of the aerodynamic and energy efficiency problems that face a lot of other animals today. And so he and I started this collaboration to examine the monarch butterfly wings to see if we could determine if the monarch wings themselves, the colors of the wings, provide any aerodynamic benefit to the monarchs during this flight. And so we approached this project in 2 different ways. And I'm going to tell you about both of them. So in the paper that comes out next week, you'll see that there are 2 different components, a first and a second, and each component sort of reinforces the previous one. So for this first component, we had this basic question here. If you look across the different cohorts of monarchs, from the summer monarchs that hang out up here, to the migrating monarchs, and to the wintering monarchs, we wanted to know, if you look closely at their wings, can you see any difference between this group, and this group? And what we were looking to see is if the black coloration provides an aerodynamic benefit, as it does with the albatross and the other birds, what we expected to see actually was that as you go southward, that the monarchs would be more black when you get to the wintering cohort. Because if you think about it, if black is really important for aerodynamics, then those monarchs that happen to be more black would be sort of the lucky ones, and they would be the ones that would be more likely to reach the wintering colonies. And so if you look across the different cohorts, we should be able to see increases in the amounts of black on average between these different cohorts. Like all of these monarchs here in the summer haven't started migrating yet, right? So this should be a collection of all monarchs, all appearances, lots of black, less black, and so forth. But as you go further southward, you're going to start whittling down the cohort until you get to the ones who are the successful ones. And so going into this, we completely expected to see the wintering monarchs would be more black than these ones. So what we did here was we capitalized on some prior experiments that had been done where myself, my wife, and some other colleagues have collected monarchs over the years in these different cohorts, these different regions. And so over the years, in all of the different studies we've done, we've almost always taken a picture or a scan of the actual monarchs that we've collected in these different regions. And by scan, I literally mean a scan. Like you put a monarch on a flatbed scanner, face down, and you hold it down with some weights, and you scan it like a photocopy. So basically, these are all like photocopies of live monarchs. And these are all in my computer right now. And over the years, I've been collecting these photocopies, quote unquote, for many years. So much so that I've probably got thousands of them on my computer. And so what we did with this project was we basically went computer diving into my computer, and we sort of extracted all of the monarchs that we could find that had been collected in the summer. We extracted those that were collected during the migration and those that were collected at the wintering colonies. So basically, we had scans of each of these three different cohorts. So that's sort of where we got the specimens from, the quote unquote specimens. They were digital specimens. But I kind of treat these like almost like digital museum specimens, because, you know, you can go back and remeasure the specimens over and over again if you have a computer copy of them. So I've got all these pictures. And so what we wanted to do then was here's a really close-up picture of a butterfly flying. I should point out one thing before I get too far. This picture is nice because it sort of shows something that that people really need to remember. Like if you go back and look at the butterfly wings at the specimens like this, it's like they're all in a sort of a pinning state where their wings are out, and you know you can see both the fore and hind wings. They don't fly like this in this shape. They actually fly more like in this shape, right, with their forewings spread backwards. And so once they're in this shape, you can see that all of the spots are on the trailing edge, right down here. And the black region along the fore and hind wings is also along the trailing edge. So that's the edge that's sort of in behind the butterfly as it's going forward. That's important to remember going forward. So I've got all these specimens, all these digital specimens. We wanted to measure the wings. And what we wanted to know was how much black is there on the wings, how much white is there, and how much orange is there? Basically 3 different colors, right? And so from those specimens, we input them into a computer program that basically calculated that for us. Here's just like a screenshot of the computer program. And it's a little complicated, and you don't have to worry about too much of this. But if you look down here at the pictures, what we did is we took the initial wing measurement. We took the initial forewing.
Her chicken's in my blackberry bush.
Miss Ramona, Miss Ramona, could you mute?
Oh, I'm sorry.
Miss Ramona, could you mute?
I should have been muted the whole time. I don't know why it wasn't muted.
All right.
What the heck?
Okay. All right. Thank you. So the monarch wings, the computer program separated them into their 3 different components, 3 different color components: black, orange, and then white. And then from those components, the computer can then calculate the percentage of that color on the wing. And that was the actual data that we wanted to see. We wanted to see if the percentage of the black gets bigger as you go further south into Mexico. So I'm next going to jump right into the results to show you the results of this one part here. This is a graph showing you how much black was on the wings of females and males, left and right there, across those three different zones or life stages: the breeding period, the migration period, and then the wintering period. And so don't worry too much about how the females differ from the males. We kind of already know that females have more black than males. What you want to look for here is to see how the percentage of black changes as you go further south in both the males versus and females. So basically, we were wrong. We found that the percentage of black gets less as you migrate southward, so that when the monarchs are at the wintering colonies, they actually have less black than those that haven't started the journey yet. And so it seems like having less black is important, not more as we thought. Miss Ramona, you are still unmuted.
That is so.
There you go. All right, thank you.
As host, you should be able to mute anybody.
Oh, thank you very much. I should have just done that.
Yeah.
Okay.
It says my microphone is muted. I don't understand it.
Okay, I'm going to try to do it from here. There you go. All right. So the percentage of black goes down as you migrate southward. That was interesting. The percentage of orange doesn't really change. We know that females have less orange than males do. Don't worry about that. But if you look across the breeding, migration, and winter, there's not really any pattern there. So basically, that means that the amount of orange is not as important as the black. It's not an indicator of migration. Now, here's the cool thing: if you look at the white pigment, the percentage of the wings that were white, there was a really clear, really strong signal here showing you that the more white you have, the better your chances at reaching Mexico. And it was really striking. Now, and it's interesting because if I back up here, the amount of black that goes down when you get to the wintering colonies, numerically, it's not that much. It's actually like 3%. So from here to here, it's only a 3% difference, even though this is statistically significant. And then going forward, the amount of white that changes is about 3%. So basically, if you have 3% less black and 3% more white, you're more likely to reach Mexico. So we were kind of blown away by that because we had no idea going into this that the white would be important at all. Because, you know, what does white do? Like, no one ever thinks white is important. And especially little spots. Like, here's a picture of a monarch. And, you know, no one knows what these spots really do. Really, there's no research on them. So we were kind of really surprised at finding this. Now, so I want you to look at something really closely here. So this is a monarch that I specifically chose here to represent what we see in the summer. Now look closely at its spots. A lot of them aren't white, right? They're white and orange, and some of them are more orange than others. And this is once I go through this and show you more of it, you're going to be like, my God, we didn't see this before? Because that's exactly what I was thinking before. Like, why didn't anyone see this before? Now watch this. I'm going to show you the next one is going to be a wintering monarch, and look closely at its spots. And then you're going to go, oh my God. I can hear you doing it in the background, even though you're not. I can't hear you, but I know you're doing it. Like, oh my God, look at that. Let me go back. Summer, Mexico. Isn't that freaky? Like, once you start queuing in on this and you have a mental picture of what to look for, you can't unsee it. It's really freaky. Like, I don't know why no one has ever noticed this before. Here's another way to look at it. Here's a breeding monarch, and then to the right is an overwintering monarch. So I've chosen the best ones here, right? Like, they don't all look like this. This is more of like a statistical thing. But once you really start looking at it and you see the difference, it becomes almost like my God, this is really freaky. So here's just some random pictures from the internet. And you can sort of do what I'm doing now. Look really closely. And these ones, these are obviously monarchs from Mexico. Look really closely at the wings, at the forewings and the hind wings on the upper side. And you can really start to see what I see as well. Like, look at this one right down here. See, really, really big white spots. I mean, they're big, quote unquote big, but they're, it's a matter of percentages here. Here's another one right here. You can sort of see that there. Another one there. It's like, why didn't anyone see this before? And if you look close, they're all like this, really large white spots. So, and then here's another one from the internet. It really shows it really well. And then this one below it, here's another one. So white spots are important for the monarch migration. Like, who knew? So we were kind of blown away by this first part of the experiment, because we were going into this thinking that we would see, darker monarchs at the wintering colonies. And so,
I have a question, if I may.
yes.
Does aging affect other animals like monarchs the way humans, where we might lose melanin or lose our hair color with age? Because the overwintering monarchs, they live the longest of any other generation. Does that affect other animals like that?
In a way, so monarchs do become, what's the word? They do become bleached a little bit in the sun, and so it's not the same as like their hair turning gray, that which was what happens in humans. But there is some fading of color in monarch wings as they are in Mexico. But we don't think that this pattern here is an artifact of fading of the color, because you can kind of see it here with this wing, although there's some other wings that it's more pronounced in. There's one here, like the fading. If this was fading, then it would be happening equally across the entire wing. And
Yeah.
so it seems like if the monarchs really are changing their spot color along their migration from orange to white, I mean, that would be just as fantastic to discover as well, really. But let me get to the later parts, because our later ideas and experiments sort of demonstrate this idea even better.
Well, thank you.
Yeah, no, that's a good question, because we actually had that in the paper. In the paper, we actually brought up this issue of bleaching and fading of colors, and so it's clearly something that was on our minds as well. So the first part of this experiment made us realize that the white seems to be really important to our surprise. So next we did this other experiment or other comparison project, where we wanted to see if monarchs themselves have larger, whiter spots because of their migration, larger than non-migratory butterflies. And so, if you think about it, there's lots of relatives of monarchs around the Americas, like the New World, that don't migrate. There's like queens and soldiers, and I'll show you a list in a minute, but there's a lot of different species and subspecies within the genus Danaus that, they're close relatives that don't migrate at all. And so we thought, well, if the monarchs have evolved this migration, and if spots are important for the migration, then monarchs should have evolved larger spots. So to do this project, we capitalized on yet another collection of digital specimens. And these were photographs of museum specimens that had been collected by a colleague. And this is my colleague, Paula Barriga. And she's a co-author on the paper. She had done a project a few years ago where she had looked at museum specimens of monarchs and their close relatives. And she happened to have photographed them in the museum, just like this. And I had access to all, she gave me access to all her photos. And we went through all the photos and we extracted photos of the Danaus specimens that she had photographed. And it turns out that she had a lot of them. And so there were specimens from queens and soldiers and Florida queens. There's a Southern monarch. There's, where's my list? These are the specimen pictures. They were all done. They're all taken like in a very standardized way and with a white background. And you can kind of see how, if you look closely at these wings, you know, all the members of the genus Danaus have a similar basic wing sort of plan where there's an orange background, there's a black border, and then there's some white spotting. They all have the same pattern, basically. Here's some more pictures of all the specimens that we measured, that we focused on. So the monarch is at the top. You've got this megalippy subspecies of monarch. This is in South America. Florida queen, striated queen, soldier, Caribbean queen, South American monarch. This one here actually has a very small migration in South America. It's been studied once, but this one is partially migratory. Keep that in mind. But you can see they all have the same basic wing pattern, orange and then black and then some spots. And so what we wanted to do was to see if the spots on the monarchs were larger than the spots on these guys, basically. And so to do that, I had this wonderful student, Christina Vu, who's pictured here, looking at a spider in my lab. And she had done sort of the grunt work on this project where she was tasked with measuring all the spots on all of these specimens. And it was kind of funny because I told her, listen, measure these spots. It's going to be a big project. But I had to convince her, right? Because, you know, who thinks spots are important? Anyway, so she took the monarch wings or the specimens. She did some tracing on the computer screen. She measured, she selected all of the outer spots on the monarchs. We were just focused on the outer edges here, not these inner ones. She measured all the spots, and we measured them in proportion to the wing size itself. So we can get a measurement that's relative to the wing size. And we did that for all of the different species and subspecies to see if the monarch's spots are larger than everybody else. So if you haven't figured it out, we found that. And here's a graph showing you what we found. The x-axis here is the spot size in percentage of the total wing size. And the monarchs are here in green. And these are the breeding, the migrant, and the wintering monarchs. And then here in this light green, these are those semi-migratory South American monarchs, southern monarch. And then these are the non-migratory species and subspecies. Don't worry about these letters. And as you can see, the monarchs have larger spots than everybody else. I mean, it's not a huge difference, but it's statistically significant. And the ones that make it to the wintering sites have the largest. So this basically confirmed what we had found initially with the first part, that spots have evolved with migration. So here's another, this is a picture that I put together for the press releases. And so you might see this like in the New York Times article that they write or wherever it's going to be. In this picture here, I've sort of shown 3 different species, monarchs, the Florida queen and the Caribbean queen. And then I've highlighted down here the lower portion, the hind wings, because that really highlights the main difference you'll see between the monarchs and then the other species. I mean, we measured the spots on the forewings because they were, because we happen to have a lot of forewing pictures. But really, the hind wings also show the main thing too, that the other species just don't have a lot of spots on their hind wings, and the monarchs do. So, yeah, the conclusion of our project is this: monarchs with the larger, wider spots are more successful during the fall migration. In addition, migratory monarchs have evolved to have larger, whiter spots than their non-migratory cousins. All of that means white spots are important for the long distance migration. Okay, so I know what you're all thinking. Why? And so for that part here, we don't have any experimental evidence. What we have is some really, really good theoretical explanations for why this is happening. But really, we're going to do some more experiments probably later this year and into next year. And so our next paper is going to sort of experimentally verify what we're just showing here. So here's our working theory. These spots are providing an aerodynamic advantage to the monarchs. And let me show you what I mean here. Let me just use this one picture. Let me just go back to where's my picture of the monarch in flight? There. So what we think is happening is that these spots, because they are positioned along the trailing edge of the monarch, what's happening is that these spots are providing lift, not lift, but they're actually influencing the air currents directly above the monarch wings. Because as we mentioned before, black is like the universal solar heating unit, right? When you have a black surface, it warms fast. But when you have a white surface, it doesn't warm. And so you get a bit of a cooling effect. And so the black juxtaposed right next to the white creates this micro eddy of air current flowing upwards, because the cooling air is meeting the warm air right next to it, which creates a small eddy rising up. And whenever you have an eddy rising up, that actually produces, it gives you less drag. And so basically what we think is happening is that the monarchs are using the spots as an aerodynamic advantage. A lot of that is going to come down to us experimentally verifying what I just said. And to do that, what we have planned is Mustafa and his team are going to build a micro wing, like a monarch wing, that they can put into a very small wind tunnel. And we're going to have it so that we can manipulate the wing colors and have spots or have no spots, and change the size of them and so forth. And then we'll sort of experimentally, put that wing in the wind and then see how that affects the aerodynamics of that wing. So, yeah, but basically what we found is that monarchs have evolved spots to help them with their long distance migration. So the thing I think is really cool about this project is because it's not only have we found this previously unknown facet of the monarch butterfly biology, but this finding, and if it bears out with further testing, actually has some real world mechanical engineering applications. I mean, if this all bears out, this means that we can improve aerial vehicle design simply by having them colored in different ways, like with spots or with zebra patterns, or with basically with paint. You can improve the flight efficiency of an aerial vehicle, like a drone or a plane or what have you. So we could actually be benefiting, like humankind could be benefiting from learning from how the monarch butterfly is able to migrate so well. So as you can see, I'm really excited about this, and it's going to be a really big project. It's going to raise a lot of eyebrows, because, as I said before, no one has ever thought to look at the colors of these wings in terms of sort of aerodynamic advantages, because no one really knows what the spots do, but no one who would have thought that they do this.
If I may,
Yeah.
because you said we can ask questions, I have sort of a question, but in a form of a comment. I'm baffled that such tiny measurement. The monarch itself is small. These spots are so tiny, and yet they're actually making a difference. But what I'm also kind of confused about is, like, if something is stationary, like you mentioned, a car sitting in the sun, if something is just stationary, and then I can understand the air around it being affected, but they're actively flying. And so while the wings are going up and down and the monarch's moving all over, it's still creating these eddies around it.
Let me correct you, because most of the time when they're migrating, they're actually gliding just like this in this actual position. So
Right. Okay.
in fact, 86% of the time during the migration, they're in this position, not flapping at all. And so really they're just like a giant or like a mini kite, and they're just sort of soaring in the wind. But this soaring, if you think about it, is positioning them so that they're getting direct sunlight all day, every day. And really the amount of solar radiation they're getting increases as they go southward, simply because of geography. Even when it's, cold outside, the solar radiation is increasing as you go southward. And so it kind of makes sense that monarchs have, over the eons, have evolved to capitalize on that solar radiation as they're flying. And really, because it's a small difference to us, maybe it doesn't make much, that maybe it's more of a compounding kind of thing, because as they're migrating southward, they're spending hours upon hours in the sunlight in these soaring positions. And so, even a small difference could be the difference between, eventually making it versus not. But that's a good question though.
That really helps. Thank you.
I'm winding down now, so if there's more questions, I'd be happy to answer them.
Have y'all done any research with this on the non-native plants and how the potential mutations might affect the spots?
That's a good question. The short answer is no. We haven't done any research, but if you think about it, now that we know spots are important, imagine what we could study in the future. Like, imagine if you could sort of go back. In fact, I probably could. I could go back right now and look at all of the butterflies that I've previously photographed in the experiments that have been done in the past, where different host plants were used. I could go back now and answer your question and look to see if the spot sizes were larger, if the monarchs were reared on tropical milkweed versus native milkweed. We could go back now and look at museum specimens, say going back like 100 years from before now, and we could go back and see if the spot sizes have changed over time. Imagine you could do this with the museum specimens now, because you can photograph them, you can measure their spots. So, but also imagine if you could measure the spot sizes of monarchs in different regions of the continent to see which region produces monarchs with the biggest spots, right? Because that would be a sign that those monarchs are really, really well suited for the migration.
Or would the monarchs further north need larger spots because they have farther to travel?
Yep, that's a good question too. So I can foresee, a whole suite of projects coming out of this one now that we've cued in on the importance of these stupid little spots.
Canadian monarchs have massive spots versus Texas monarchs have tiny spots.
Yeah, maybe. So now, before you go looking at your monarchs in your backyard, let me tell you that you're probably going to see a whole gamut of monarchs, some that have large spots, some that have small spots, some that have orange, and what have you. You're going to see the whole gamut, right? It's more of a statistical thing. So on average, what we might see is that the spots tend to be larger in Canada, right? But you will still see monarchs with small spots in Canada, but on average, they will tend to be larger. So just because you see a big spotted monarch in Texas, that doesn't sort of counter this entire project. So you have to do these things in with large sample sizes. And especially since these differences we're seeing here between these different groups are like small in terms of the amount.
Hey, Andy.
Yes.
So when you were saying that, I did most of my stuff until recently on the overwintering sites in California. And so I'm going through all of my pictures to see that's a much shorter distance if they travel in the west than they do in the east, or are they all white too? And every picture that I'm seeing from the overwintering sites, they're all white. Now, I can't tell the size versus other sizes, but I thought that was interesting. And then it made me think that when I started trying to draw monarchs, I was always doing all of my dots always white. And then I'd see another picture somewhere and it have oranges in it. And I thought, what? And now that's because all I ever saw, because, at the overwintering sites where I was, we didn't have breeding monarchs. We only had the overwintering months there from October to March. So that was interesting.
I think like I said, once you see it, you can't unsee it, right?
This also makes me wonder, because I've seen butterflies, if a predator has taken a nip, out of their wings and they have little chunks missing and stuff, that could possibly mean they don't make the migration. I mean, for multiple reasons, but I'm kind of, my mind is thinking of other factors and things that this affects, or that affects their migration and stuff. And this is a really cool study. Thank you so much for sharing it.
Sure. Yeah. Well, the predator taking a nip out of the wing is it's a little bit of a different topic than what we're talking about here. So when they're, I guess what I'm trying to say is monarchs that have wing damage usually don't make the migration anyway because of the damage to the wing. And it's probably not because of the spots being missing, but it's more like the aerodynamics of the whole butterfly is thrown off. I mean, I remember Lincoln Brower used to tell me that whenever he would go down to Mexico and look at the clusters, he said there's nothing but pristine monarchs everywhere, like nary a tear anywhere in any of the monarchs that you see. But yet, if you look at monarchs during the fall migration, or the ones during that haven't started yet, there's rips and tears and in random places and in lots of monarchs. But at the wintering colonies, no, everybody's perfect. And so that was my first cue to make me realize that, yeah, the aerodynamics are really important here.
Ramona wants to ask a question, and so you need to unmute her.
Oh, yes.
Can you hear me okay?
Yes.
My apologies about the chicken and the blackberries.
That's all right. I have chickens.
My neighbor's chickens are eating my caterpillars too. What I wanted to ask was about the vacuum chambers. I've worked with them in the past, and I know you're doing flight dynamics and trying to look at that. Will you be able to set up different UV intensities and look at the UV light as well and how it heats with the radiation effects?
Yeah, that might be on the docket in the future. A lot of that is going to be. I'm going to leave that up to my colleague because he's got all the gear and the gizmos and the tech for that. My expertise in this is sort of on the monarchs themselves, the measurements of the wings, the color. And so he does all the flight stuff. And so I know he's got, like, what does he call it? PIV. Like they put the wings in these tunnels. They put fog in there so they can see the airflow around them.
But you're looking at radiation and heat effects too, so somehow you'd have to take that into account as a variable.
Well,
Just wanted to add that.
What he does is he actually builds heating elements into his wings, so he can actually heat the wings in different places. And so he already did this once for a bird wing. He made this little miniature bird wing, and he put heating elements in them in different places around the wing to see where, because actually it's a good segue, because he found that when you heat up the trailing edge of a wing, that provides the most aerodynamic benefit to a winged animal. And if you think about it, that could explain why monarchs have black along the trailing edge, because this black is heating up in the sunlight. And so that this might explain even why the monarchs have this very pattern that they do. So, yeah, I'm going to leave a lot of that up to him. I always like it. I always enjoy watching what they do over there from a distance. Like whenever I zoom with them and look at pictures of their stuff, it's like something out of Tony Stark's garage, right? There's gizmos and gears and tubes and people doing stuff, and it's really fun. I'm going to wind down here. Maybe if there's one last question, I'll take it. But if not, I will. We'll get rolling here. I actually have to. I got to meet with somebody from National Geographic in like 20 minutes here.
This is just so cool. It's amazing. I'm sitting here imagining thin films of air going past the wings and the eddies. It's just. I know how I'm going to spend my afternoon. I'm going to be looking at wings.
It's been fun for me to experience this project because myself, I've never really considered the aerodynamics of these wings either. And I don't think a lot of other butterfly researchers have. In fact, I don't think there's any researchers of butterflies that are studying aerodynamics. And I think this is going to open up a lot of eyes.
Andy, as you see links, as you see the various things that you've posted or appearances that you've made, if you could post a link on the Thoughtful Monarch, that'd be great.
For this
topic. Yeah.
This topic. So I will post one of my blogs when the study comes out.
Excellent.
And that will describe basically what I've told you guys already. And so that will be on the Thoughtful Monarch for sure. And if you guys wanted to, you could share that. There will be articles everywhere. You can share those. Feel free. As far as this recording goes, I'm going to put this online somewhere, but I do want people to sort of go through the exercise of sharing some science. So
right.
I think that's sort of the idea here. I don't want people to sort of just share the link to someone who doesn't really do anything to get it. So I want to thank you guys for showing up today, and thank you again for being part of the Thoughtful Monarch group. And yeah, I'm excited to tell you guys about this.
Thank you. This was great, and there were some really good questions too. So,
Awesome.
Yeah.
Thank
All right,
you.
guys.